as Alina said, I'm located at the New York University in Abu Dhabi as part of the Center for Space Science. Today I'm going to talk to you about the sun, the stars, and particularly the interior of them. And when I was designing the talk, I was wondering how much of an introduction to give, because I understand that the solar physics department are in the mathematics. So it's going to be very introduction heavy, probably for around half of it, but I hope you can get an appreciation of solar physics and seismology that we use, and then how we use that in the sun and the stars. So in case you're wondering where Abu Dhabi is, this is where you're located here in Australia, and this is where Abu Dhabi is located. Very hot. I think at the moment it's around 40 degrees, but with humidity it's near 50 degrees. So quite warm compared to here. It's quite a shock to come back to the cold weather. Okay, so the sun, just as a quick recap, the interior of the sun consists of the core, the radiative zone, and the convection zone. You've probably seen it in your undergraduate studies. The reason we care about the interior is that everything is connected in the sun. Okay, so everything you see on the surface, all the space, wherever, it all originates in the interior. Okay, so we need to understand the interior dynamics, the physics, the magnetic fields, the convection, and in doing that, by understanding our own sun, we can get an appreciation of what's happening with other stars. There's quite unique laboratory conditions that are very unattainable here on Earth. For instance, there's densities and temperatures that are just very difficult to replicate here, but also in numerical studies. So we often, as with physics, you come up with a theory, you also need observations to constrain your ideas. The problem is that the sun and other stars are optically thick at the surface. So we can't use conventional astronomy, we can't just look in some electromagnetic band and see the interior of the sun. We have to rely on seismology. So the sun and the stars are very noisy. They've got a lot of sound waves inside them. And so we infer the properties of the interior of these stars through observing the waves that travel within them. As I said earlier, there are problems with, on the simulation side. I understand a lot of you are a bit more numerically focused, but simulations are possible, but we often face the difficulties due to the extreme conditions. So here I've plotted the density, and you see how where's this stick? Here we are. This is logarithmic scale here, and you can see that the density rapidly drops. So we often have difficulties in solar physics understanding what's happening in the interior, because it's very hard to numerically compute grids that vary from large scales down to very small scale dynamics very quickly. And so often where observations are ahead of the game when it comes to understanding the sun. So today's talk will be mainly about observations. So as I said, we need to see the interior of the star, so we rely on stellar waves. And it's roughly been 60 years since the first acoustic wave was detected in the sun in the 60s. They're thought to be generated near the surface. So at the surface of the sun, there's a lot of rapid turbulent convection. And these convective cells generate sound waves. And these sound waves propagate into the interior, and then they come back to the surface. Now, unfortunately, you might see some blurring here, some movement. It's a small video. I'm sorry for those at the back. But those are the sound waves. So as the sound waves come up to the surface, they bounce off the surface and go back into the interior. And we can observe these oscillations of the surface, and that tells us about the sound waves within. For the sun, the period of the sound waves is typically around 5 minutes or 3 millihertz if you're spectrally minded. But for other stars, depending on the structure, the peak of your oscillations may vary. And typically, we observe our observations through Doppler images. Anyway, and because we deal with waves, we don't generally work in the spatial and temporal domain. We often work in the spectral. Yes? Sorry, I'm
sorry for interrupting you. I was wondering what sets the period of the oscillations?
The structure. So depending on the sound speed and the density structure of the star, depends on the period.
But what's the spatial scale, right? So the period is presumably some spatial scale divided by the sound speed, right? So I understand what says the sound speed.
No, there's a temporal scale and then there's a spatial scale when it comes to the acoustic waves.
Like the thickness of the outer layer of the convective shell?
No, we'll get to the spatial scale of these sound waves in a moment. But yeah, there's a lot of scales going on, a lot of different scales for the sound waves as well. I just flopped the slides around. I was just getting to that point. Okay, so typically when we have stellar waves, we think spectrally. So we try to decompose them onto a new basis. And we typically use spherical harmonics, or we can use Fourier transforms. Some of you may be familiar with them, but if you wanted to take a wave pattern you observed on the sun and decompose it, you could decompose it into spherical harmonics. And here I've ripped this image off Wikipedia describing spherical harmonics. So if you had an oscillation that was purely spherical, the whole star was coming in and out, and there's no nodes, we describe them by two numbers, L and M. L is the number of nodes the wave has in latitude, and M is the number of nodes the wave has in longitude. So if the star is purely pulsating spherically, you have L equal M0, okay? But then different waves have different number of nodes in latitude and longitude, and so they have different components. And that's typically how we describe global waves of a star. Now, if you take the Doppler images of the sun and decompose them spatially into spherical harmonics, but then you also do a Fourier transform in time, you start to see the temporal and spatial scales of these acoustic waves. So you get this lovely diagram. It never looks like this in reality. This is well edited afterwards. But you see these defined ridges of power in your power spectrum. Here, L, remember, is the number of latitudes, the number of nodes in latitude, but it's also the inverse of the spatial scale. And what we see is defined ridges of power, and these are different types of acoustic modes. And these are what we use in our seismology. So you have, typically you have something called the F mode. This is actually surface gravity mode. This stays very close to the surface, doesn't go very deeply, okay? Then you have the acoustic modes, and we call them P, pressure waves, P modes, and they go on from here. So 1, 2, 3, 4, 5, okay? Typically, waves at this end of the spectrum, so up here, very shallow waves that don't go very deep. Waves down this end, or low frequencies, they go deep into the star. Does that kind of answer your question?
I'm still not sure. Okay, there should be some simple physical equation I should be able to write down to allow me to get it roughly 5 minutes, right? And I'm trying to figure out what that equation is.
Let's talk afterwards, because I feel like this will detract. But yeah, let's talk afterwards. Okay, so there are waves all over the sun. Some are shallow, some are deep. So if we could take a slice of the sun, you can see the acoustic waves. They typically come up, or they start at this. Let me use a stick so you don't see my hand everywhere. Let's say you have a source term, which we don't exactly know what the sources are of the acoustic waves, but you have a source of your acoustic waves. And if you plotted the ray paths, they would travel into the interior where they experience an increase in density, increase in sound speed. And because of that, they start to refract and they come back up to the surface, which they may bounce again. Okay? They'll always keep bouncing on the surface. And these are the P modes that I was talking about, but there are also this set of G modes, which are gravity modes. They are observable in other stars, but in our sun, we can't see them because they're typically constrained in the interior. The reason I bring up these G modes is that I'll be explaining a bit later about coupling between between a certain type of waves and the gravity waves. But what you need to know is that the G modes, the gravity modes, are typically in the interior of the star, and the acoustic modes are on the exterior, near the surface. Okay, so that's great. Waves are traveling all around the sun. So how do we actually use them for imaging? So as I said, you have a wave, goes in the interior, comes back. But say, for instance, you have some perturbation, something missing in your model, say a flow, a magnetic field. As the acoustic wave travels into the interior, it will pass through this inhomogeneity compared to your model, and the waves will be altered. Typically they can change in amplitude, they can be damped, they can scatter. But either way, the wave changes from our understanding of the model. So we can actually measure these changes from the power spectrum I showed you earlier. And by doing so, we can actually infer what's happening below the surface. Let's skip that part. Oh no, sorry. So we can actually infer what's happening in the surface. So the first question is observations. Now, you start with observations, you observe something, you observe a shift, then you need to figure out what's happening below the surface. So in terms of the sun, there are typically two types of solar physics groups. There's the ones who examine the interior, so we use sound waves, and there are those who observe the exterior. They can see the exterior, and they're more interested in kind of space, weather, magnetic fields. Okay? Now, we use Doppler images, and we typically observe the iron 1 spectral line. Now, this spectral line shifts depending how the surface of the sun shifts. Remember, the sound waves, they bounce off the surface, so they cause small shifts in the Doppler images. We measure these Doppler images, and we get an image like this. Now, you may see red here and blue here. This is due to the rotation of the sun. So the sun is rotating this way. That means this part of the sun is moving away from us. This part of the sun is moving towards us. But you also see this small scale pattern here. And these are the sound waves. So this is sound wave moving the surface towards us and moving away from us. And then, of course, magnetic regions. Now that's how we observe the sun. The question is, how do we observe other stars? We generally have a couple of programs, the Kepler, TESS, and Plato. Plato hasn't launched yet. But they observe the intensity images of other stars. And you may have seen this when it comes to exoplanets. You'll see a dip as the exoplanet passes in front of the sun. But if you take this time series, do a Fourier transform, you'll see the acoustic modes. Okay? Now, how these acoustic modes behave tell us about the structure of the sun, and we'll get to... So now we have all our observations in hand. I'll just skip this part. The question is, how do we determine this? So let's say we have perturbations and we assume they are small, and they're called small shifts to the wave property. So we're in the linear regime. We're not definitely trying to keep it easy for us. There are non-linear cases, but typically we deal with linear cases in the sun. So you have your observable. Let's say we observe, I don't know, frequency shift or amplitude shift. This is related to the unknown perturbation through this equation. So the unknown perturbation multiplied by what are called sensitivity maps. Now, I could go into details on how these sensitivity maps are derived, but all it does is it tells you how much your observable changes due to a perturbation. So let's say this is a flow, right? Waves that travel with the flow travel faster, waves that travel against the flow travel slower. So this little map, the kernels, they tell you how sensitive your sound wave is to a perturbation. So we solve this problem. This is usually done through inversions, using least squares, etc. But that's how we can measure flows, magnetic fields. That's basically how helioseismology works, and also how astereoseismology works. With asteroseismology, we tend to deal with the larger scales because we can't see the stars quite well, so we have to think globally. But with helioseismology, we think locally, so we can see quite small structures. Now, I'll quickly explain one of our techniques, because in that way you can get in a slight appreciation of how we do it in practice, but also this technique is quite important for the results I will be speaking about momentarily. So as I said, we observe Doppler images, and let's say we cut a little patch out of the Doppler image, and we track it for 1 day. Okay? We then get a data cube. We do a Fourier transform in all 3 directions, or you can do a spherical transform in the spatial direction, but you just transform all 3 directions, and you get a slice of the power spectrum. Remember earlier I was showing you the ridges? Well, in 3D, this is what it looks like. You've got the ridges coming up, but then if you take a slice in the frequency domain, you get these lovely rings. Okay? As I described earlier, if you have something that is in the way of the waves as they travel into the interior, they will change the properties of the wave. So as the wave comes across the flow field, it will be sped up or slowed down. And so if we take a slice into the board, so we take a slice into the board all the way around the outer ring, if there is no flow, this ring should have a constant frequency. But when in reality there are mean flows, and so we see a deflection in the frequency of the wave. So waves traveling westward are shifted, have a negative frequency shift, and flows traveling eastward have a positive frequency shift. We measure all of these, and we get these parameters, which are, let's call them virtual flows. The flows needed to move this particular acoustic mode by that much. You make all the measurements of all the rings, and then the true flow at a chosen depth is a linear combination of these virtual flows. Okay? And so typically with this technique, and with most helioseismology, we're actually constrained to near the surface because acoustic waves are very surface sensitive. But we can choose deeper down, but we face noise problems. And it's a constant battle in our field of trying to balance the signal to noise, but also trying to observe short-lived things. You can't observe it for too long, but you need to get some good time series in order to get a good measurement. Okay, so one measurement is kind of like the most successful measurement we've had in helioseismology and in astereoseismology actually, is the sun's differential rotation. So the sun rotates faster at the equator than it does at the poles. It typically takes 25 days for the equator to rotate all the whole way around, but at the poles it takes around 35 days. This rotation profile, depending on the frame that you track your Doppler images, induces frequency shifts. We can measure these frequency shifts, and we can measure the differential rotation not only as a function of what it is on the surface, we can observe it in the interior as well. So somebody did that in the 90s. They measured all the frequency shifts, all the observables. They solved that little integral problem that I showed you, and they got the differential rotation as a function of latitude and as a function of depth. What was interesting is that in the convection zone in the sun, so the outer 30% of the sun, the rotation is radially differential and latitudinally. So the high latitudes rotate slower, the low latitudes rotate faster, but also there's this shear. So right near the surface, they rotate slowly, but just below the surface, they rotate fast. If you keep solving this problem all the way down, once you hit the convection zone, the radiative boundary, so around 70% of the sun's interior, the sun becomes solid body. So the interior of the sun is solid body rotation, but the exterior is differential. And this has recently been extended to other stars. So some researchers at my center, they applied similar techniques to astroseismic data. So they were interested, how many other stars rotate like our sun? And what they found is that most stars above a reasonable probability threshold rotate the same way as our sun. So other sun-like stars rotate faster at the equator than at the poles. But this is a big problem because if you think of, say, a figure skater, okay? When their arms are out, they rotate slowly, but when their arms are in, they rotate fast. You apply that to in the theory of the sun, because the equator should, in theory, be rotating slower than the poles, because the different distance from in order to conserve momentum, the distance from the higher latitudes to the rotational axis is smaller than at the equator. So you should, in theory, have the opposite. We call it anti-solar rotation, where the poles are rotating faster than the equator. But our sun and other stars are rotating faster at the equator. Why is that? Something must be transferring momentum from the higher latitudes to the lower latitudes. And it's all very, as I said at the beginning, everything is connected because this differential rotation profile lends to the solar activity cycle we see. And I'll explain that in a bit, but everything is connected. Okay, rotation, the waves, the magnetic fields. Okay, so now I'm going to talk about, that's the end of the introduction. Any questions at this point? I don't want to lose you at this point, okay? So now we talk about the discovery of solar inertial waves and why it's important to everything I've talked about before. So inertial waves, a classic one is the Rossby wave. So inertial waves are a type of wave that exists in rotating fluids, okay? And one of them, and probably the easiest to understand, is the Rossby wave, or they're known as inertial waves or planetary waves. These are very large scale waves, okay? We're talking on the scale of the body, whether it's the Earth or the Sun. We see Rossby waves in the Earth's atmosphere, and we also see it in the oceans. So in the Earth's atmosphere, you might have seen this, the polar vortex, or the undulations on the edge of the polar vortex, which may lead to extreme weather conditions in the northern hemisphere. These undulations are an indication of the Earth's atmospheric Rossby waves. And also in the Earth's oceans, a team in the 90s measured oceanic Rossby waves. Now these are very small amplitude. We're talking amplitude of 4 centimeters on the ocean, right? Well, it's actually below the ocean, but the Rossby waves are well known to exist here on Earth in both the atmospheres and the oceans. They typically propagate retrograde. So if the Earth is rotating this way, then the Rossby waves moving on the opposite direction. They have a positive group speed, which means that I'll explain that bit in a second. But the classic indicator of a Rossby wave or one of these inertial waves is that they travel in the opposite direction to the rotation. And the frequency at which they travel, we always talk frequencies instead of travel times. The frequency that they travel is often related very closely to the rotation of the Earth. Okay, so you know, if you derive some equation for the rotation rate of these inertial waves, usually the rotation rate of the planetary or stellar body is a term that's in there. Okay, so solar Rossby waves, we see them on Earth. They have been seen in Jupiter, or at least loosely seen in Jupiter. So, and we know they should exist in stellar bodies. So the question is, do they exist in the Sun? So in 2018, a team at Max Planck discovered solar Rossby waves. So what they did is they computed all those flow maps. So they measured all those flows like I described before. They then compute the radial vorticity, because inertial waves are usually vortical, so they're transverse. They usually don't have a radial component. They remove systematics, which is always a problem when you deal with observations. And they removed them as best they can. I don't think you can ever truly get rid of systematics with real data. They did transforms, and they looked at the power spectrum. So when you do a Fourier transform, the power spectrum is just the square, modulus squared of the signal. And they see this thing. Down the bottom, we have the azimuthal order m. So remember, m is the number of nodes in longitude, and then they have the frequency. Now the frequency is negative here. Negative frequency means it moves in the opposite direction to rotation. Okay, it's just a convention that we use. Anything above this line moves in the direction of rotation. Anything below moves in the opposite, retrograde. And they found that they got this power. Now this solid line here is theory, and theory derived in the 1980s. So it was remarkable that the observations matched very closely to the theory. And as I said, this is azimuthal order m. And what they found, is it in the next one? Oh yeah, I'll get to that in a second. Sorry, I've jumped ahead of myself. And since the discovery in 2018, there have been a number of follow-up studies where we confirm them in other observational techniques and other observational data. So these results are very clean. Basically, this is as clean as you can get in helioseismology. You've got a signal and your background is very, very small. There's no question about whether this is a signal or not. But things get a little bit weird. So solar Rossby waves, back here, there should be a full spectrum of them. But we only see L equals M. Okay? Remember, L and M are the number of nodes in latitude and longitude. We only see L equal M, which means we only see equatorial Rossby waves. In theory, Rossby waves should exist all over the sun. High latitudes, low latitudes, symmetric, anti-symmetric. The only Rossby waves we see are symmetric equatorial Rossby waves. These are the vortices. Okay? So that's a bit strange. And then the L equals M, 1 and 2, so very large scale Rossby waves, don't exist. Don't know why, they're just not seen in the sun. They should exist, but they don't. So it's a very weird thing. But the biggest question that came out from the observations of Rossby waves is, can they play a role in the differential rotation of the sun? Remember I said the sun is rotating faster at the equator than it is at the poles. The question is, can these Rossby waves help in transferring angular momentum from the higher latitudes to the lower latitudes, enabling the sun to maintain a fast equatorial rotation rate? But there was a theoretical study that came out and said, yes, Rossby waves could be the only cause for this transport of angular momentum. The thing is, Rossby waves are not the only thing that are in the sun. There's magnetic fields, but there are also other inertial modes. So this was a study that we've recently got published in Nature Astronomy, and we discovered another set of high frequency retrograde vorticity waves in the sun. Now this is a very long name, and that's because we don't know what they are, but it describes exactly what they are. So if we look in the power spectrum again, and instead of looking at the symmetric component, we looked at the anti-symmetric component. So you've got clockwise rotation in the northern hemisphere, anti-clockwise rotation in the southern hemisphere. And you look at the power spectrum. These are very noisy power spectrum. The red line are the Rossby waves we saw before. The purple line, which runs right through this enhanced power here, indicate where the waves that we have detected are. So what we see is this enhanced power along this dark ridge here. Signal to noise is very poor, just above 1 kind of thing. And these are equatorially anti-symmetric. So again, we're not at high latitudes, but these inertial waves are close to the equator, but they're anti-symmetric. The interesting thing is that the frequency is much more negative than the Rossby waves, meaning they are moving retrograde a lot faster than Rossby waves. But if you look at the theory, the fastest, purely hydrodynamical, the fastest a Rossby wave or an inertial wave should be able to move is this red line. All other inertial waves and Rossby waves, sorry, that's not entirely true. All other Rossby waves should be above this red line. Anything below this line is something a lot more complex. It's an inertial wave mixed with something else. The question is, what is it mixed with? Now, as a final note on this slide, because the signal is so weak, when you have a really weak signal but something very interesting, you have to compare it to all your other observations you have and all the other techniques. So we compared, this is all the HMI data, which is our recent satellite, and this is the ground-based data. And what we found is this signal is consistently in all the data, whether it's over cycle 23, so 2010 to 2020, or the last 24 years. The signal is always there. And it very much stays on this 3 times. So it's 3 times the frequency of the Rossby waves. So for those who are spatially minded, this is a video of what's happening. So these are the Rossby waves, the ones that were discovered back in 2018. They're equatorial, they're symmetric. They sit on the equator and they rotate. These are the waves we found here, moving a lot faster, a lot weaker, and anti-symmetric. So the question is, how can these waves be moving faster than Rossby waves? Well, they have to be coupled with something. And there are three options on what these waves are coupled with. They have to be enhanced by some other physics rather than just hydrodynamics. So the first question is, are they coupled with magnetism? The sun is a magnetic star. It's very active and it's got a very strong magnetic field. Now, there's a lot of theory out there that says that inertial waves, Rossby waves, could couple with the magnetic field, somehow altering and produce a new set of magnetohydrodynamic waves. These waves could be traveling faster, they could be traveling slower, but it's a new set of inertial waves, and maybe this antisymmetric wave we've seen are these coupled waves. So as I said, the sun is a magnetic star. It has a cycle of 11 years, so it goes from no surface magnetism to high surface magnetism, solar storms, SpaceX, you better watch out, to back to quiet period. And this repeats roughly every 11 years. We have enough data from our observations to cover 2 of these cycles. From 2020 back to 1996, we have 2 cycles. The interesting thing is that the sun is not consistent with its magnetic activity. For instance, this cycle, cycle 23, was very active, but the one that followed it, the one that we've had in the last 11 years, was very weak. Okay? But how does the inertial waves couple with the magnetic field? Well, if you assume that during the quiet period, the sun is like a bar magnet. It's got purely poloidal fields. The field comes out, goes around, comes back through the south. Okay? This is a very simple image of what's happening. As the cycle goes on, the differential rotation causes a drift in this poloidal field, and you start generating toroidal field, which is a field that goes around in longitude. It's thought, in theory, that during this period, the inertial waves, because they interact with this toroidal field, generating magnetohydrodynamic waves. So the question is what we're seeing these kinds of waves? Well, certainly, if you take the shallow water MHD calculations, you could certainly get near the frequencies we're interested in. So this is the Rossby wave. These are the I call them HFR waves. That way I don't have to repeat high frequency retrograde all the time. So these are the HFR waves. Now, if you took a toroidal field that looks something like this, and this is a reasonable, simple but reasonable guess, you can see that the frequencies, you can certainly get a lot more retrograde than you did before. But you also get 2 sets of waves. You get a retrograde, blue and red lines, and you get prograde, blue and red lines. And the blue and red just tell you about the magnitude of the toroidal field. And in MHD, this is known as the fast MHD wave, and this is known as the slow MHD wave. So if these waves are MHD waves, we would expect, maybe, if it's possible above the noise, a second branch of power in the prograde direction. We played around with as many configurations as we could get, and we couldn't really shift the Rossby waves down to this ridge. They typically tended to bend like this. But that's okay, maybe our theory is poor, and so we go back to the observations and have a look. So as I said, we've got 2 cycles of solar magnetism. As the magnetic cycle moves on, there's more toroidal field, so we expect stronger enhancement of the Rossby waves. If we cut up the data, look at different data sets, look at different time periods, and plot the central frequency of these HFR modes, we expect that these frequencies would shift. If they were magnetic in nature, they should be shifting, okay? So during a period of high magnetic activity, they could be down here, and during a period of low magnetic activity, they should be closer to the Rossby waves. What we found is that no matter how we cut up the data, or what data set we looked at, the frequency was consistent, okay? And here I've plotted in, I didn't include the legend, the red is cycle 23, and the black is cycle 24. Remember, I said cycle 23 is twice as strong as cycle 24, so you would expect some reasonable frequency shift here, but they look rather consistent. So we can conclude that it is unlikely, can't outrightly cross it out, but it is unlikely that these waves are magnetic in origin. We also looked in the...
What's the blue bit in here?
That's just a central frequency, just so we know how much we can show how much it's shifting. So this is a central frequency for the full data set, and these are the power spectra of the data set divided in two. And you can see that they're not really shifting that much from the mean frequency. Sorry, I've lost my train of thought. Don't worry. So yes, we've ruled out that it is unlikely that they are magnetic in origin. Okay, but there are still other candidates to be. Gravity modes. So we talked about gravity waves. They're in the interior of the sun. Is it possible that the Rossby waves are coupling with gravity, producing a new set of gravity inertial waves? These are known as Yanai waves. They have been seen in the Earth. But there are a couple of problems with that. In order to generate such waves, you need to have a transition region between where the Rossby waves are in the convection zone and the gravity modes are in the interior. This region is what's known as the tachocline. It's been observed to be around 2% possibly of the radius of the sun. But if you do some quick theoretical calculations, in order to get the frequencies that we observe, the transition region would have to be incredibly small, a lot smaller than the observations of this transition region are. Okay, but you know, they still could be gravity modes in some weird misunderstanding of the physics. But also the theory outrightly says that these waves have to be symmetric, and what we're seeing is very strong anti-symmetric signal. So the fact that anti-symmetric and the fact that the theory disagrees with the observations enables us to at least say it's unlikely that these are gravity inertial waves. So the last contender is convection. So these are the big three things in the sun: gravity, magnetism, and convection. The sun has a convection problem, okay? You have a large convection zone that is the outer 30% of the SAR. You expect to see all kinds of scales of convection. So convection is hot material rising, cooling down, and sinking, okay? At the surface, we can see very small scale convection. So these are very shallow, very small. They're pumping out a lot of heat. And these are known as granules. We also see supergranules, which are typically on the scale of 30 megameters. Still small compared to the sun, but large compared to the Earth. So these two are the scales of convection we see in the sun. In theory, we should see a much, much larger scale of convection on the order of hundreds of megameters, so comparable to the sun at the size of the sun. Okay? These are known as giant cells, giant convection cells, or thermal Rossby waves. Okay? Numerical studies consistently say these things should exist. There is theory that says these things should exist, and for 60 years we've never seen one. There have been plenty of papers that have come out saying, I've detected thermal Rossby waves, but they've ended up being disproved. Okay? The sun has very weak large-scale convection. Not sure why. Maybe it's a misunderstanding of the structure of the sun. It doesn't take much. You can actually alter the model of the sun just a little bit and these things will disappear. But we don't know why. But if you were to do an observation like we did with the inertial waves, they would look very much like what we see. Case in point, thermal Rossby waves will look something like this. Here is the radial component, but it can also be the divergence. So hot materials coming out, and they kind of look like columns that pierce the surface of the sun. And what you should get anti-symmetric vorticity. So thermal Rossby waves, according to numerical studies and theory, should be anti-symmetric. Fantastic. We have an anti-symmetric signal in our data. These must be the same. Problem, no matter where you look and no matter what you do, the theory and the numerical studies say that the thermal Rossby waves must be prograde. Our waves are definitely retrograde. Okay? So our waves are moving in the opposite direction. But again, maybe the theory is wrong, the numerical studies are wrong, so we go back to the observations. If they're convective in nature, they should be raising hot material. Okay? So there should be a radial component, a divergence. As hot material comes out, cools down and sinks. There must be a divergence. So let's have a look at the divergence. We were looking at the vorticity before. If this blue line is where the signal is in our vorticity, we don't see much power on it. We see some power above it. We don't see any power on it. If these waves are divergent, we expect there to be power on this line. This signal here, you might be wondering, well, maybe it's just that shifted. This signal is actually just a systematic from the magnetic field. So this is magnetic field signal, and that's just a systematic. Okay, so we have no divergence. The waves are moving in the opposite direction to theory. So again, we have to rule out thermal Rossby waves. So all three of our options, magnetism, gravity, and thermal Rossby waves, no longer work. Well, what else is there? Well, there's not much left. Okay, so something in the sun, we don't want to say there's exotic physics. You know, within reason, there's nothing in the sun that could be, is that unlikely to be causing it. Okay, well, maybe we don't know what's causing them, but are they important? Remember, we talked about Rossby waves. They could be transporting angular momentum. These waves are on the same spatial scales. Are they also transporting angular momentum? Does it complicate the picture? So the way that angular momentum would be transported is what's known as the latitudinal Reynolds stress. And it's just basically the mean of your latitudinal flows times your longitudinal flows. So these are the Reynolds stresses of Rossby waves, and these are the Reynolds stresses of the Hfr modes. Whilst the Rossby waves are stronger, they're not that much stronger than the Hfr modes. So if you were to start building a picture of how angular momentum is transported in the sun, you would have to include both the Rossby waves and the Hfr modes. So they are important, at least in that picture. What also complicates it is that you need to also include convection, so supergranules, and you also would need to include magnetism if you were trying to figure out how this angular momentum is transported. But the point is that the Hfr modes could be as important as the Rossby modes when it comes to building that model. Last thing is, can we actually learn anything about the interior of the sun from these Hfr modes? So as I said, the signal gets weaker as you look deeper in the interior. These waves that we look at typically are at the surface, but they should have some structure below the surface. So can we learn anything about the structure by looking at these waves? Well, almost immediately after we published the paper, somebody quickly wrote up a numerical code, and they say that if you just put the solar model in, add a little bit of viscosity and differential rotation, you can see the Hfr modes. Now, there is some debate whether these guys have done the right job. The problem when you do numerical studies is that it's basically an eigenvalue solver, and you do the calculation. There are eigenvalues all over the spectrum. You've got to choose which ones are the most physical, and you can, if you want, hand pick whatever you like. Okay, so there's some debate on whether this is true, but it's interesting that they can get inertial waves with frequencies similar to what we observe. So there is some hope that maybe through numerical studies or parameter searches, we could get down to what's causing these Hfr modes. There's something about the structure of the sun that we already know about, but what exactly about it is causing these new inertial modes to behave so differently compared to the classically known Rossby waves. So that wraps me up. So the outlook is inertial modes could shed light on large-scale dynamics like rotation, also structure. We know that there's rotation in other stars. There is a possibility that we detect at least one or two Rossby modes. It is possible using of other stars. So we may learn something. How different do other stars' Rossby modes look compared to what we expect? The origin of the Hfr modes is still unknown, but future modeling is promising. There's around 3 groups rushing to try to figure it out at the moment. And but what's also interesting is that we use acoustic modes right now to image the interior of the sun. But these acoustic modes are very restricted to the surface. we could also measure the changes of these inertial modes from the theory. So the Rossby modes match the theory, but not exactly. Maybe we can use those measurements and infer about the deep structure of the sun a bit better. And so that's the new direction I think our field is going in. It's inertial mode seismology. That's where we are. That's where we're at in the field. And thank you. Any questions?
I think I might have mentioned this, but why, in 2019 when they, I guess, found the Rossby modes in the sun, why weren't the Hfr modes waves also found?
The data they were using was very short time period. And in order to improve your signal to noise, you need to have a long time series. More time series, more waves you will see, okay? And the signal was so weak that when they looked at it, they couldn't see it. In fact, there's nothing special with it, like, you know, I don't want to diminish my work, but there's nothing special about what we did in terms of the observations. They're sitting there. We just happened to have the right data set at the right time, and we looked at it and went, right, are they in the other data sets? Let's start looking at long time series, and they started popping out.
I maybe got a little bit lost there, but are you suggesting that these Hfr waves result in the angular momentum transport?
No, they may play a role.
Would that be purely like a latitudinal angular momentum transport, or would it have some effect on the radial?
There are semi-analytical models that suggest that the amount of transport changes radially. Okay, but the transport is transverse, latitudinal.
Yeah, cool.
But in theory, you know, these Reynolds stresses that I showed are a bit on the small side to maintain the differential rotation. But those stresses increase as you go deeper. As the density increases, so do those stresses. And maybe most of the transfer is occurring much deeper.
So does meridional circulation play a role in transporting angular momentum?
No, because there's no phi component. It's purely in one direction, and it's the stresses are due to the two components, the latitudinal and the longitudinal component.
Same question, but just like asked the other way, what does do the angular momentum transport in the sun?
What does it?
Yeah.
So it's thought that it occurs through the Reynolds stresses. So if you plotted the eigenfunctions.
Actual viscosity.
No, it's due to the, depends on how you look at it, but if you plot the eigenfunctions, I don't know, tell me if I'm getting too technical, but there's an imaginary real part which implies that there's a shear and of the components, and it's thought that, viscosity is thought to be played, but we don't know the viscosity of the sun, basically, that well, at least in the interior. And it's thought it's the latitudinal Reynolds stress term is thought to be a component, but not.
So where does that come from? That comes from microscopic viscosity.
No, it comes from the perturbations to the mean. So the Reynolds stresses, right, is just if you consider your flow field as a mean plus something else. Yeah.
Is it solved or is this unsolved?
It's completely unsolved. Completely unsolved. You know, there's numerics, there's observations. They don't match. Nobody knows what's going on.
So you mentioned that we can also do this, or possibly do this with other stars.
Yeah.
What's the actual time series length that you need?
Well, the thing is, yes. So other stars we don't observe for that long. So if we manage to get a long time series, you can do it at 2 years, maybe 4. If you've got a candidate in there that you observe for that long, in theory, yes. The problem is the modes that you can observe with other stars are very large scale modes. L equals 0, 1, 2, okay? These Rossby modes are 3 onwards, okay? Now, typically you can observe scales half of your wavelength, maybe. Okay, so in theory, you could see a Rossby mode at 4, even though you've only got 1, 0, 1, 2. You could see 1 at 4 in theory. Whether it's possible, I don't know. We'll have to try.
I guess you mentioned that probably other solar type stars kind of behave the same, but I was wondering what happens if you have a slightly lower mass star which is more convective, or maybe even fully convective, or maybe to a larger, slightly larger mass star which actually maybe has, maybe it's also fully radiated.
I don't know what will happen.
Yeah. Any other observations on that?
So the Rossby modes are linked to the rotation rate of the star. Okay, it's not really about the convection, it's about the rotation rate of the fluid. So if you knew the rotation rate of these other stars, you could guess where their Rossby modes would be. But I don't know what to expect with lower mass or higher mass stars. Is that the question?
Some theory that expects some differential rotation in different mass stars, depending on the...
Oh yeah. I would expect differential rotation of some form in other stars, in different type stars, but it hasn't been done. The calculations, because we don't know the origin of the weird differential rotation. We also can't guess what a certain size star would be doing.
Questions. I think I have also a different follow-up. I think you mentioned that in the ocean the amplitude of the Rossby wave is very small, like I think a few centimeters. What's actually the amplitude of the Rossby waves on the sun, and maybe also for the retrograde?
Yeah, so the amplitude of the Rossby modes on the sun are around 1 meter per second, because we measure 1 meter per second up and down, and then the Rossby modes are around 30% of that, so just under a meter, very close to the noise background. When we talk amplitudes, we're talking the horizontal flows required for said measurements. Mm-hmm.
Could you explain again why thermal Rossby waves could exist and why you don't see them in your...
So thermal Rossby waves are the same thing as giant convective cells. So you expect if you had a box, top and bottom, you would have a convective cell, hopefully, maybe, of the size of the box, going from the bottom to the top. That's what these giant cells are, is that there's some large-scale, slow-moving, hot material from the base of the convection zone to the surface. And that's what these, and thermal Rossby waves are just a bit more of a specific term for these giant cells. They kind of appear as Bhutan-esque columns around the sun. They're just large upflows and vorticity, etc.
And so is it because of the fact that the frequency of this would be like much lower than your...
So the numerics and the theory says it should be prograde, but they're retrograde. But you ask any observationalist and they say, oh, I don't believe in numerics or theory. But the point is that the coupling, you could couple between these similar frequency modes. Maybe they are thermal Rossby waves, and that it would be enhanced or different to the Rossby mode. So it's why it was a candidate, is that basically these frequencies aren't the Rossby modes. That must be enhanced by something. What are the possible things that it could be enhanced by? And convection was one of them.
There's a question on Zoom land from Simon Campbell, and he asked, are we assuming the sun is spherical? Would not sphericity change the wave properties?
Yes and yes. You've got to make assumptions somewhere. Yeah, when we do a spherical... Well, how technical can we get? We are assuming a spherical harmonic series. So we're assuming the sun is spherical, these waves are spherical. But in reality, these waves aren't captured by spherical harmonics correctly. And so there is a bit of leakage. And leakage is often the case when you make certain assumptions on the geometry of what you're doing.
Simon says thanks. Right, so any other final questions? If not, I think we can thank our speaker again.
Thank you.